Hey again, Florian here. This time I will give you a little intro to Kubernetes and why we chose it as infrastructure for SOGNO. Most of the video will make sense without context. Note, however, that this is part of a series describing how to install an example SOGNO service. This video can be thought of as first introduction to Kubernetes. It is not essential to running a service, so if you just want a service running or if you are already familiar with Kubernetes, this video is likely not for you. Also note that some things might be a bit oversimplified or leave out some details that are not essential to understanding the basic concepts. Let's get started on the topic. Often when we run a program, we don't really care what machine it is run on as long as it can be reached and runs out of the box. Anybody that has installed specialized software like solvers and the like can tell you that the latter part is quite more involved than it sounds. This is usually due to conflicts in versions and libraries. So for example, if you have two programs and one requires version 1.3 of a library and the other one version 2.1, you need to point them both in the right direction and you need to have both versions of the library installed, which can yield conflicts. To deal with that, applications are often containerized. That means the program itself, together with all dependencies and even the operating system, is bundled together in an image. This image can be run as a whole, and the program is thus executed in almost the exact same environment every time, reducing the complexity of deploying the program. This also has the advantage that the program is run in a kind of sandbox, adding a layer between the virtual environment and the hosting machine. The most well-known tool for containerization is Docker, which can be used to create images and run containers. We also use Docker to create our images, however, we will run the containers on Kubernetes. Now, let's go one step further with our abstraction. If we already don't have to care about the configuration of the host machine, then why would we care on which host exactly it is run at all? This is what Kubernetes provides. Your program will be run in a container on any machine that is part of the Kubernetes cluster. If you are following this tutorial, the only machine in the cluster is the one we installed K3s on. For a full Kubernetes cluster, that is not true. That can have many machines, so-called nodes. The nice thing here is that it doesn't really make a difference whether we add another machine later on. This part of the management is mostly abstracted away by Kubernetes. Also, most cloud providers have a Kubernetes option allowing one solution to work for multiple hardware setups. Kubernetes does all that using the so-called Kubernetes resources. A resource is a configuration file in the YAML format that defines what is supposed to be run and how, if that's even a question. Kubernetes will determine the difference between the current and the desired state and create everything accordingly. The resources we will have a look at here are namespaces, pods, replica sets, deployments, services, ingresses, and secrets or config maps. First, let's talk about namespaces real quick. They are meant to separate concerns between different working groups or applications. Naming conflicts between resources in different namespaces don't occur, and it is possible to assign access rights to namespaces as well as resource limits. For the other resources, I will show you very basic resource files to illustrate how they should be used. There is, however, no need to follow along or look at every detail. I personally use the Kubernetes extension in Visual Studio Code that provides snippets for all basic resources. Let's start with a pod. A pod can be thought of as a virtual machine itself running one container. Technically, a pod can run multiple containers, but nothing to worry about. If the container ever crashes or becomes unexpectedly unresponsive, it will be generally restarted automatically. This is what a basic pod specification looks like. We have three places where we can add the name of the pod, for example, test pod, as we want. Then we can define an image, for example, from Docker Hub. We can define some resource limits, and also we have to specify what ports the container should respond to. If you change the definition of a pod, Kubernetes will start a new pod with the updated configuration and will shut down the old one once the new one is running. Pods also give the ability to set labels for one pod, as seen up here. For example, the name of the pod, which is pretty default. These labels can be used by Kubernetes to identify which resources belong to each other. Note that a pod is just one instance of a program. If you, for example, host a web server with static content, it is easy to imagine that you would like to run multiple pods of these to spread the load of the server between multiple machines. This is what is called horizontal scaling and is made very easy in Kubernetes. You will rarely handle pods directly, but usually higher units that manage those pods. This is where the replica set comes in. The replica set defines a template for a container and lets you set a number of replicas you need. Kubernetes will then look up how many pods are running that belong to that replica set and start and stop pods accordingly to the difference. This also holds if pods become unavailable because a cluster node goes offline. If you change the container template, a completely new replica set will be created. The old one is scaled down to 0 replicas. This is much more convenient already. However, replica sets too are rarely handled directly. This is why we are not looking at the resource definition for replica sets. Instead, we usually define deployments. This is what a deployment looks like. A deployment is basically a replica set. However, it is persistent between changes to the container template. If the template is changed, it will create a new replica set with a new template. Since the deployment is not recreated, it allows to keep a history of updates and versions. This means that changes to the deployment can be rolled back. The deployment is usually the key resource people work with. If we have a look at the resource definition, we can see that what we saw before with the pod is exactly what we see here with the template. And everything would be put in here, just as we did with the pod. Note as an example that we are here setting a label with app, my app for the pods created by the deployment, and also matching this label by the deployment. We will see this label again in a second. Next, let's have a look at the service. The service can be thought of as an address of the set of pods. Usually it provides access to all pods of one deployment. It does that by forwarding each request it receives to one pod that matches the label specified on the pod. More concretely, it allows us to match the name of an application and thus all pods of the application. Any request to the service will then be forwarded to one of the pods. This is what I showed you before. This selector specifies app, my app, so it will forward to all the pods that are created by the deployment, where the pods also have the label app, my app. However, how do you address a service? That depends on the type. The default type for a service is cluster IP. A cluster IP service is not reachable from the outside directly at all. From inside the cluster, it can be addressed by its name or namespace/service name. So for this service, it would be something like, can be addressed directly as my app, or if we create it in the default namespace, default/my app. The second type of service is node port. We can change to a node port by just adding type node port. This kind of service will be assigned a port to the outside world. This kind of service will be assigned a port randomly in the range from 30,000 to 40,000 unless a specific one is defined in the YAML file, which we can do under ports and node port. And then, for example, 30,001. This, however, is not recommended, since then we have to coordinate multiple node ports from multiple namespaces with each other and avoid collisions. With the node port, any request sent to that port is forwarded to the service and then to the pod. After we define this node port service, it is exposed on all nodes of the cluster on exactly that external port. Any request sent to this port on any of the nodes is forwarded to the service, which itself forwards it to all the pods matching its selector. The node port comes in handy in development as it does not require a domain name and can be used directly with IP. The remaining two types of services are load balancers and external name service, which we will not cover here. As a small disclaimer, please be aware that the word service has multiple meanings in software development, and I will do my very best to differentiate between Kubernetes resource, service, and other meanings of the word service. Building on the service, we can use an ingress to make our application available via domain name from outside the cluster. It allows to configure the usage of TLS and the routing of different subdomains and URL paths. So we can use one URL for multiple services and route them depending on the path. This way, the possibly quite complex setup of pods and services will be easily accessible under a single URL. A usage of ingress without a domain name is not possible. Using a node port is probably your best bet. This is what an ingress resource definition looks like. We can define our host URL here. And then we can use the path to route specific paths to a specific service. We just said we can address this as the app name, which was my app, and we need to specify the correct port here again. The last two resources that we want to talk about are secrets and config maps, which are closely related. These two resources are basically key value storages that provide data via environment variables to the pod. For example, passwords, but also endpoints for different services that need to be addressed, for example, logging or message brokers. The nice thing is that any number of pods can use a single config map, so it is guaranteed that they are synchronized. Same goes for secrets, of course. The secret only adds a layer of encoding to the config map, so it is not directly clearly readable. This is, however, a simple base 64 encoding, so anybody with access to these values or the namespace in which they are saved can decode them easily. This is what a config maps look like, and it's very easy. We just put a key and a value here. We can have as many as we want. And they can be provided to a deployment. Okay, this concludes our small overview. I hope this was a bit helpful in understanding the idea behind Kubernetes. In the next video, we will install some Kubernetes resources in our Kubernetes cluster that belong to our PyMFM service. It is not necessary to understand Kubernetes to a bigger extent or even remember everything in this video, but I hope you will recognize some things in the next video. See you there.